5 is about Newton's third law. This is his final law of motion. But before we can talk about it, I want to talk a little bit more about forces. We know that a force is a push or a pull. But one thing you may not have thought about is anytime you have a force, you have an interaction between two objects. It's not possible for there to just be one object and be a force. A gravitational force is an interaction between an object and the mass of the earth. If I go over here and I push on this wall, I exert a force on this wall, the wall is exerting a force back on me. If I have a textbook, here's a textbook, can't really see it, but it's sitting on this table right in front of me. It's pushing on the table is pushing back up. Anytime you have a force, there has to be two objects. We often call this an interaction pair. Okay. The other thing you have to realize is that there's always two forces. We have two objects, but we also have two forces. So all forces come in pairs. And I guess this is really what I mean when I talk about the interaction pair. Rephrase it. There's an interaction between two objects, and as a result, there's two forces. A lot of times people will call this an action force and a reaction force. We need to be a little bit careful though when we use those words, because it sort of implies when you say action, reaction, that this happens first and this happens second, but that's not what happens. They happen at the exact same time. It is an interaction. So we know all forces are a result of an interaction between two masses and that there are two forces. Now, the crucial idea is the forces are the same magnitude, but are in opposite directions. If I push on this wall with a force of 40 newtons, this wall is pushing back with a force of 40 newtons. I happen to be pushing that direction to my right, which means that the wall is pushing back on me to my left. If we have a horse and it pulls on a cart, if the horse is pulling the cart to the east, well, then the cart is pulling on the horse to the west with the exact same magnitude of force. Those forces are equal, but they're in opposite directions. All right, all of this together really brings us to Newton's third law. And Newton's third law says whenever one object exerts a force on a second object, The second object exerts an equal, opposite force on the first object. This is the law that you probably learned in middle school, is that for every action, there is an equal but opposite reaction, using that idea of an action force and a reaction. But what we want to remember is it's an interaction. They take place at the same time. It's really easier to write Newton's third law as a very brief equation. The force that A exerts on B, so we have two objects, A and B, whatever force A exerts on B is equal to the opposite of the force that B exerts on A. All that negative sign does is indicate direction. If A is pulling B up, then B is pulling A down. Now, one of the things that comes up a lot, especially when you start thinking about things like horses and carts, or a tow truck pulling a car, if the horse pulls on the cart and the cart pulls back equally on the horse, don't those just cancel out? How does anything ever move? How does a tow truck pull a car if the car is pulling back with just as much force? To answer those questions, we really need to understand a couple of things. First of all, we have to remember that these forces are acting on two different objects. So each object can be considered separately. And we have to understand what the system is that we're talking about. So let's look at a picture and let's talk about a system. A system is a collection of objects. Most of the time in discourse, when we have a system, it's going to be a very small system. It'll consist of one or two objects. I don't even think we'll ever look at a system that has three objects, but we might. It's usually a very small system. Okay. So let's go back to this idea of a horse and a cart. Now, I'm no artist, so we're going to keep this really simple. So here's a cart. And I'm pretty sure I can't draw a horse, but we'll draw an animal-shaped something. Oops. And there's a horse. Oh, could have been worse. I'll give it an ear and I'll feel better. All right, so we've got this horse and this cart connected. There it is. The horse pulls on the cart pulls on the horse. If we want to know whether or not something accelerates, we just look at the net force on that object. If I want to know if the cart accelerates, I need to only look at forces on the cart. I'm going to look at just the cart. So if my system is the cart, and I can see that the net force on the cart is not zero, it's going to accelerate. So here's my cart. Just draw it as a dot. I have the pull from the horse, and I probably have a little bit of friction back here too. But if I'm only treating the cart as my system, if the pull of the horse is greater than the force of friction, then Newton's second law tells me that cart has to accelerate. Okay? Now, I can make the system bigger. I can say, let's not just look at a system of just a cart. Let's look at a system that includes the horse and the cart, because we know most of the time, not just the cart accelerates, but the horse and the cart accelerates. If I look at this whole thing as a system, and I want to know if the whole thing will accelerate, well, in order to accelerate, the net force, the external forces, have to be non-zero. Well, the pull in here between the horse and the cart and the cart and the horse, in this case, since they're both part of the same system, they do cancel out. If the horse pulls on the cart with 100 newtons and the cart pulls back with 100 newtons, they're going to cancel out. We call those internal forces. So I could say, if I look at the horse-cart system, that the interaction between the horse and the cart is internal. It's inside the system. They do cancel out. But you go, well, then why in the world how does the horse make the horse-cart system accelerate? Well, think about what happens when a horse tries to pull. He doesn't just pull on the cart. When a horse pulls a cart, he also pushes against the ground. In fact, if you think of the horse here, he's going to push with his feet against the ground in a direction like that. When he tries to pull the horse, he's going to push against the ground. What happens if the horse pushes against the ground? The ground pushes against the horse. The ground is going to push like this in the opposite direction. Okay, well now we see there's a net force acting on this horse-cart system. The net force is the ground pushing against the horse and cart system. So now the whole system will accelerate. Okay? So if you want to know whether or not something will accelerate, you look at the object. If we only look at the cart will accelerate because of the force from the horse. But if we look at the whole horse-cart system, we realize that the horse is accelerating and bringing the cart with it because the push of the ground onto the horse. Okay? Really important to pay attention. Anytime you want to know what happens to an object, you want to look only at the forces that are acting on that system or that object. Most of the time, we'll just let that object be one thing and we'll look only at the forces. We don't usually look at forces exerted by the system. We don't care about the force the horse is exerting on the ground because that's by the system. But we care very much about the force exerted by the ground on the horse because that's a force on the system and that causes our acceleration. Okay, well, let's think about how these action, reaction forces affect different masses. Well, there's a couple of really obvious ones. One you might think of would be a bullet and a rifle. I'm not really a marksman, but most people in East Texas have probably fired a rifle at least once. You think about it, if you want to know, there's a force that happens internally inside the rifle that exerts a force both on the bullet and on the rifle. If you're not careful when you hold a rifle, and I don't even know how to hold one really, it will kick back into your shoulder because it gets that recoil velocity, because there's a force that's equal but opposite. So you can think about, here's the rifle, it's the, don't know how to draw along, there's a rifle, and here's a bullet. The mass of the bullet is really, really small compared to the mass of the rifle. They feel an equal force. If you think about it, the force of the rifle on the bullet is equal but opposite to the force of the bullet on the rifle. In other words, these two objects feel the exact same force. The rifle feels a force back into your shoulder. The bullet feels a force this way. But they have very different accelerations. The reason they have very different accelerations is that acceleration is equal to the net force divided by the mass. Well, what's going to happen? If the mass is very large, that net force is going to give you a very small acceleration. So if I'll get a little tiny acceleration, if I divide by a great big mass. The larger this mass is, the smaller this acceleration is going to be. So the heavier this rifle is, the smaller that recoil acceleration. However, if I have a very small mass, what I'm going to find is a very small mass can give me a very large acceleration because I have the same net force. This net force and this net force are the same, but I'm dividing it by a very small mass. This is our formula. When this mass is really large, this acceleration is going to be really tiny. But when this equal force didn't change the size of the force, but if that mass is really small, it's going to experience a really large acceleration. So a bullet has a really large acceleration compared to the rifle that fired it. The force between these two is exactly the same. Now, look at that same principle. Suppose you have a coconut and it's falling out of a tree. Coconut might have a mass of 1 kilogram, which means it would weigh about 10 newtons. So here's the earth. It's very large. Here's the coconut. It's very small, but it weighs 10 newtons. The weight of any object, whether it's a coconut or a person, a rock, is an interaction between that object and the earth. The two objects, anytime you talk about weight or free fall, the two objects you're talking about, one of them is the earth, and the other is whatever is falling or whatever is being pulled down by gravity. Or even if it's not moving, this book still weighs 20 newtons or so because gravity is pulling down on it. So This one has a downward force of 10 newtons, and the earth has an upward force of 10 newtons. The earth is pulling on the coconut with 10 newtons, which means the coconut is pulling on the earth with 10 newtons in the opposite direction. Those forces are equal in magnitude and opposite in direction. You see the coconut accelerate. It has an obvious acceleration, but you don't see the earth accelerate. And there's a really good reason. If we have a 10 Newton force, remember acceleration is net force divided by mass. If the net force is 10 newtons and the mass is 1 kilogram, that's our coconut's going to accelerate at 10 meters per second squared. Everything near the surface of the earth is going to accelerate with that. However, what does the earth do? Well, first of all, the net force on the earth is probably not 10 newtons because there's coconuts and apples and kiwi fruit. There's things falling on all sides of the planet, so a whole lot of that would cancel out. But even if it didn't, even if the only force on the earth was 10 newtons, if I have a 10 Newton force pulling the earth up, and the mass of the earth is approximately 6 times 10 to the negative 24 kilograms, that's going to come out to be about 1.7 times 10, oh that's positive 24, sorry about that, 10 to the 24th kilograms times 10 to the negative 24 meters per second squared. Remember we said when that exponent is negative, it's a really, really small quantity. So this is a quantity that would start off with a decimal point followed by 23 zeros and then a 1. That's an incredibly small acceleration because that's an incredibly large mass. Okay? Just because you can't really see how the force is pulling up on the earth doesn't change the fact that that force is there. It's always equal but opposite, which is why on that last slide I said there are no exceptions to Newton's third law. If you see a tow truck pulling a compact car down the highway, the force the tow truck exerts on the car and the force the car exerts on the tow truck are exactly equal. If you see a baseball player and he swings his bat and he hits that baseball and it goes flying out over the fence, the force of the bat on the ball and the force the ball exerts back on the bat are equal. Same thing with a golf club. If you swing a golf club, the force of the club on the ball is exactly equal to the force of the ball on the club. Every single time. In fact, you can't exert a force on something any greater than its ability to exert a force back on you. Try and throw a feather really far. It seems like it might be easy. You're really strong, and the mass of a feather is really light. But when you try to do it, it won't go that far. You can't exert enough force. And that's because the feather can't exert enough force back on you. You're limited by how strong because it's not capable of exerting much of a force back on you. Okay? There's no exceptions. Anytime you have two objects and they are interacting, there is a force between them. The force acting on each of those objects is exactly the same size. Every time. No exceptions. And that is Newton's third law. Okay. Now, one idea that they also put in the back of this chapter is a little bit more information about vectors. We've already talked about when we add vectors and they're the same direction. Let's just practice that for a minute. For adding vectors. And want to pick some easy one. If I do a vector that is 3 meters, oh, let's use newtons, 3 newtons, and another vector that's 4 newtons, and they're pointing in the same direction, the resultant there is a 7 Newton force. But if I have a situation, let's put where I have something pulling 4 newtons this way and 3 newtons that way, when they're in opposite directions, I know I have to subtract. And this gives me a net force of 1 Newton to the right. Now, if I had drawn the larger vector over here, I could have ended up with 1 Newton to the left. And then finally, we can think about what happens if they're perpendicular. If I have 4 newtons this way and 3 newtons that way, they are going to add together. Well, usually, if you want to add them, we'll usually go from the tip. It's going to give us a force. We'll put our 3 Newton right there so we can see how they add. And we can see our resultant. There's our resultant. It would look like that. To get our resultant, we know we use the Pythagorean theorem. We would say 3 squared plus 4 squared equals the resultant squared. We end up getting 25 is equal to r squared, so r must be 5 newtons. That 3, 4, 5 is one you probably remember from high school. It's an easy one. Notice the smallest you can ever get with a 3 newtons and 4 newtons is what you would get when you subtract when they're opposite. The strongest net force is when they're in the same direction. But it's possible to get anything from 1 Newton to 7 newtons. They don't have to be perpendicular, but we don't know how to do the math when they're not. But I can kind of draw one. You can see if I had 4 newtons and then 3 newtons at an angle, this resultant is going to be less than 7. I know that because straight line would be 7. It's less than 7. It's definitely more than 5, and it's definitely more than 1. The problem is to get the length here, we have to have an understanding of trig, so we're not going to worry about that at all. I just want you to understand the smallest it would ever be is 1 Newton, the greatest it would ever be is 7 newtons, and you do need to know how to add things when they're perpendicular. Perpendicular vectors use the Pythagorean theorem. All right, vector components. Again, we're not going to do the math for vector components, but I want you to understand what they are. If you have a vector, let's say a force vector, and it points off at some angle, part of that vector is trying to pull the object up, and part of that vector is trying to push the object over. We call those the horizontal vertical components. You can see that if I were to draw kind of a shadow straight down, this vector has a component, we'll call it Vx. If this is vector V, then this is how far it's in the x direction. I'll tell you what, let's change it to a force vector because we're talking about forces. If this is some force, this is the x component of the force. The y component is how far is it trying to pull it up. You'll notice both the x component and the y component are less than the full force. All of the force is not acting to pull it forward, and all of the force is not acting to lift it up. Part of it is, okay? If we do the Pythagorean theorem, this squared plus this squared would give us back our original vector. We'd need to kind of know how to work in reverse. There is kind of a consequence about that, and this applies to normal forces or support forces. mass that's sitting on a table, we know there's two forces acting on it. We have its weight pushing down, and we have a support force. The book uses the term support force. It's also called a normal force because it's perpendicular to the surface. So we have this normal force. We know that when things are at rest on horizontal surfaces, that the weight and the normal force are equal. Because the object's not, like this book sitting on the table, it's not accelerating into the table, it's also not levitating up. Those two forces have to be equal. Okay, let's put it on an inclined plane. If instead I put it on an inclined plane like this, I tilt my table. I know that gravity always acts straight down, so the weight is still straight down. And I know that normal forces act perpendicular. The normal force will actually push this way. Okay. But how large that normal force really depends on the components of the weight. If I draw this, you can see part of the weight is pressing the box against the plane, and part of the weight is trying to pull it down the ramp. We usually call this one Wx, the weight that's trying to pull it down, that force, and this is Wy. Notice Wx and Wy are components, and they're both less than W. So what we see here is that now the support force or the normal force is less than the weight. All of the weight is not pressing against the surface. Only some of the weight is pressing against the surface. Some of the weight is trying to make it roll down the ramp. If we make it even steeper, if I tilt it all the way like this, well, now, if you think about it, none of the weight is pressing against the table. In fact, the weight is straight down. There's no force against the table. If I tilt the table all the way, the normal force will completely disappear, and now the normal force is equal to 0. There's no support force because this table is no longer supporting this block. In fact, the block will be in free fall in all likelihood. Okay. All right, let's just do a quick recap of Newton's 3 laws. The first law is the law of inertia. And it basically says if the sum of all the forces is equal to 0, that's an equilibrium statement. All the forces add up to 0. Or you can say if F net equals 0, the motion will not change. If the net force is 0, there's no acceleration. And so what happens? The object remains at rest. That's static equilibrium. If the object is static, if it's already at rest, it's going to stay at rest. Or continues to move in a straight line at a constant speed. Anytime something's at rest, I know I can add up all the forces and get 0. But anytime something's moving in a straight line at a constant speed, I know I can add up all the forces and they'll equal 0. This moving is called dynamic equilibrium. But you can be in equilibrium whether you're at rest or whether you're in motion. Okay? Sometimes, like I said, sometimes the moving part bothers students, but it does not require a force to keep motion. Things naturally remain in motion if the net force is zero. Okay? The second law is probably easier. The second law just says that the acceleration is equal to the net force divided by the mass, or this, F net equals mass times acceleration. The second law tells us what happens when the net force isn't zero. Obviously, if I put in zero here, the acceleration would be zero. But the second law tells me what happens when the net force isn't zero. Well, when the net force isn't zero, things accelerate. And then finally, that third law tells me that every time there's a force, there's actually two forces. Forces are a result of an interaction between two objects. And the force that A exerts on B is always equal, but in the opposite direction of the force that B exerts on A. If you really understand Newton's three laws, and sometimes we think we understand them, but we get a little confused, it's pretty easy to understand why things move the way they move. All right, that concludes Unit 1. If you have questions, email me. I hope you all do great on the first test.